Okay, so how is everyone today? Good, I hope. Okay, so the homework thingy is fixed, so that's good. I'll start posting homeworks today. The first ones will be due Friday. For several lectures in a row, we're not going to have any quizzes, just homeworks, and then we'll get back to quizzes during lecture. So good. I'm so happy about that. Good. As a review of last time. From last time, we talked about relations. So you can look at the previous material to see the exact definition, but just as a cursory reminder, they are things that have a domain, a range, and a mapping. And really, the only constraint, the only requirement, is that every element in the domain maps to at least one element in the range. To make a vending machine analogy, this means that every button produces at least one item. So it would be like the kind of vending machine where you walk up to it and you press button 8 so that you can get a candy bar, but in fact it produces a candy bar and also a celery. Okay, so such a thing is a relation. 2. Then we talked specifically about functions. So a function is a relation where every element in the domain maps to, so far it's exactly the same as a relation, but here's where it gets different. Maps to exactly one element in the range. So to make the vending machine analogy again, this is the kind of vending machine where every button produces one item. Right? This is in contrast to a vending machine that's a relation where every button can conceivably produce multiple items. You might imagine like a vending machine made by a concerned mother, right? Every time you press the button for a candy bar, you also get a toothbrush, right? That kind of thing. Such a thing would not be a function; it'd be a relation. Good. Then we went on to say that we're specifically interested in the word injective. In a specific kind of function, so injective. So a function is injective when every element in the range is mapped to at most once. All right. The vending machine analogy here. The vending machine analogy is that if you walk up to a vending machine, the vending machine is injective if for every item that you can obtain, it is the case that there's only one button you can press. So if you really wanted a celery, and button 8 produces a celery, then there's no other button that produces it. But if it was just a function, you know, maybe button 8 and also button 88 would give you the celery. That means that if an item is obtainable, then it is obtainable by only one button. Obtainable by exactly one button. You know, because well, notice that in the definitions and in the vending machine analogy, if you walk up to a vending machine, you know, it might have lots of delicious things in it, like maybe your favorite candy bar, but it might be the case that there's no button to press to get it, and it's just on there teasing you, visible, but you can't get it. All right, so something is a vending machine is injective if every obtainable item is obtainable in exactly one way. 4, surjective. A function is surjective when, okay, so the constraint that we wrote up here for injective was every element in the range is mapped to at most once. So I'm going to write another constraint in red here, but it's different. What is the constraint?
At most one.
That's what it was right here. Oh, yeah. At most once. So what is this one? At least once. So every element in the range is mapped to at least once. Once. The distinction is the at most versus at least. So to make the vending machine analogy, every visible item is obtainable. But there might be more than one way to get it. So you know, maybe you really want maybe you see a candy bar in there, and that's your favorite kind, and you can get it by pressing button 8. That's great. But you may also be able to get it by pressing button 87. Also. Okay. And then the last word in this family of words is bijective. So a function is bijective when what?
At least once and at most once.
Good. So both injective and surjective. And notably, if you say, I'm thinking of a number, and that I'll give you some hints. The first hint is that the number I'm thinking of is at least 1. Also, the number I'm thinking of is at most 1. Okay, well that's enough to say exactly what the number is. The number is 1. So then every element in the range is mapped to now exactly once. So to make, I won't bother writing the vending machine analogy, but I'll say that it is, in a sense, the least confusing kind of vending machine. Right? So it's a little bit confusing if you walk up to a vending machine and look at an item, and there's more than one button you can press to get it. If that whenever that happens to me, I think, wait, does it matter? Which one should I press? That's kind of confusing. Another confusing thing is that if you walk up to a vending machine and you see something that you like, but there's not a button to press to get it, that's a little bit confusing too. A bijective vending machine is like, you might think of like as a properly manufactured vending machine.
So I was thinking, well, why don't, it seems like the easiest way to say it, say the definition of bijective would be to just say it's mapped to only once. But that doesn't necessarily imply that every element in the range has been mapped to.
Right. Well, yeah. In the end, the distinction is that you know, in specialized fields where people want to mince words and parse, you know, real carefully, like in legal and math, those mean certain things. Exactly means to a mathematician. Exactly once means at least once and at most once, whereas only means at most once.
Right.
There's lots of little words like that where mathematicians want to, yeah, and that's one of them. Okay, good. So here's a function can be defined by an expression. So we talked about that last time. Can be defined by an expression. So, for example, f of x is x squared minus 6. When the domain of the function is not explicitly given, the domain of the function is the natural domain of the expression defining it. Okay, so for example, if I say, again, that one, f of x is x squared minus 6, then I can ask, well, what's its domain?
I was going to say, plus or minus 3. The set of numbers, including plus or minus 3.
Okay. So can you remind me? So the expression defining this function is x squared minus 6. So the question in the end is, what is the natural domain of that expression? All reals. What can you plug in there? What can you plug into x squared minus 6?
Plus or minus Well, you could plug anything.
anything.
Yeah. Yeah.
We're not trying to solve an equation. We're just asking what inputs can you provide? Any. So the natural domain of x squared minus 6 is the reals.
I think what throws me off is the phrase, the domain of the function is the natural domain of the expression defining it. I was trying to
Parse what that means.
force that into meaning that only the values for that particular function that are true. That's not
Okay. Whereas I could ask a question like, give an example like this. How about g of x is x squared minus 6, and then I'll say on domain 1314 to 2018, and then I'll ask what's its domain. Yeah, it's right there. We wrote it down. So to be clear about the distinction here, notice that what this is, in the first place, notice that these two functions are defined by the same expression. They're both defined by x squared minus 6. When you give an input, the function says, okay, thanks, and then it calculates x squared minus 6. However, g, we say this. So this is the explicit domain. As a result, the domain is that. Notice that for f, the domain is not explicit. As a result, the rule above is invoked, and you say, oh, well, if it's defined by an expression and the domain's not explicitly given, then the domain is understood to be the natural domain of the expression defining it. It's a mouthful. Okay, so then 3. Are functions f and g equivalent? And has a d in it. That is to say, are they the same function? So are they the same?
I would say that I can't answer that question because I don't know if the domains must be the same in order to state that they're equivalent.
So the answer to that question is yes, the domains must be the same.
No, they are not equivalent.
Okay, good. They're not the same. Not equivalent. Not equivalent because the domains are different. Now, let me say it in a different way. Let me say it with vending machines. Suppose that we have two vending machines, and they start out as identical, right? Two different ones, and they both contain the same items. They have the same buttons, and everything else. And as it happens, they both have 13 buttons. And then I come up with my tool belt, and I take one of the vending machines and I disable 5 of the buttons, so that, for example, you can no longer press button 1, 2, 3, 4, or 5. They're removed from the machine. Are these two vending machines the same? No, right? Because I took the buttons. So, concerning this, I could say, well, for example, can you plug in f of, say, 1400? Can you do that? Yeah, right? I'll do it real quick. My calculator tells me that the number is 1959994. I'll just take its word for that. Can you do G of 1400? Yeah. What's its value?
19519.
Right, same value. Okay. Can you do f of, I don't know, 4? Yeah. What's its value? 10. Because, well, you square 4 and get 16, subtract 6 and get 10. What about g of 10? No, not 10. 4. That's the point. This is undefined. Which is to say that, no, in fact, G does not have a button 4. F does, but G doesn't. Okay. So they're not the same. Good. So I'll call this, this, well, I'll just make a new remark now. So again, with a function defined by an expression. A function defined by an expression has range all of reals when not explicitly specified. Explicitly specified. Okay, so for example, I could say this function f of x is x squared minus 6. Well, and that's all that I say. Then I could ask, well, what's its domain? All reals. It's all reals because there's nothing that you couldn't plug into that expression. What's its range? All reals. Whereas I could say, for example, this one, new function, h of x is x squared minus 6 on the range, say, negative 100 to infinity. Then what's the domain of this one? All reals, right? Because we didn't explicitly specify the domain. That means that the implicit rule is invoked, and you say, well, what is the natural domain of that? Oh, it's all reals. And then for this function h, what's its range? All right, negative 100 to infinity. We wrote it right there. That's its range. Okay, so now for those of you who've taken a math class before, like college algebra, it's somewhat likely that you have a slight question mark in your head. The reason is because of the way that range is defined. Now, I hope to remind you that there was a point in the semester. Where we wrote something like this: 13 equal 14, and then asked, "Is that an equation?" And about half of you Of those of you that said anything, at least half of you said, no, it's not an equation. In fact, it is an equation. The distinction is that the thing that wasn't made clear to you before is that, yes, that's an equation, its logical value is false. So it may have been the case that formerly in your head, equation meant an equation whose logical value is true. This is an equation. Its logical value is false. All right. So there's a similar kind of thing going on with range. So remark. The image of a function is the largest subset of the range to which the function is surjective. Okay, now I'll admit it. This is a math definition that only a mathematician could love, right? Sort of like the phrase where you look at a baby and see that it's not so attractive, and you could say, "Oh, that's a baby's face that only a mother could love," right? So what I admit it. Here's a definition that only a mathematician could love. All right. So to make the vending machine analogy, you could walk up to a vending machine. That's a function. In the sense that every button produces one output. But it might be the case that one of the items, there's actually no button you can press to get it. Like maybe you really wanted that Snickers bar, but there is no button to get it. Well, the Snickers bar is in the range because it's visible, you can see it. But it is not, what? It's not in the image. Not in the image. So to make the vending machine analogy, this is the set of all items which can be obtained. In your previous math classes, it is very likely the case that the instructor at the time did not make the distinction between range and image and used the word range only and meant image. Okay, so it is like, being in that class is like living in a world where every vending machine you walk up to, if there is an item, then there's a button. But that's not really the case, right? Because I've had the sad experience of walking up to a vending machine and in fact, no button. Okay, there's a distinction between these two things. Now let's. I admit that this is pretty abstract. Let's work on it with some concrete things. Okay. So I'll say let f of x be x squared minus 6. In the first place, let's make a table. So I'll take x values -4, -3, -2, -1, 0, 1, 2, 3, 4. So we've made a table that looks like this before, but never with a function. But I imagine you can probably guess what I want. for every one of these x values, I want you to plug it into the function and tell me what it evaluates to. Okay, so in the interest of time, I'll get started. If we take -4 and plug it in, -4 squared is 16 minus 6 is 10. Okay, so that would be 10, and then 3, and then -2, -5, -6. So that's nice. And then from here, it's pretty easy because now you just have to do it in the reverse order. -5, -2, 3, 10. What I want you to see is that those red numbers read the same going forwards and backwards. When you have a sequence of items that are the same traversing it one way as the other way, that sequence of items is called a palindrome. So, you know, like dad and mom, those are palindromes. So we could now plot y is f of x. The reason why I take the time to mention palindrome is that when you have a function and there's part of it like that reads as a palindrome, that means that when you plot that part of it, there's going to be a symmetry. So when we plot it, there'll be a visual symmetry. Now, under normal circumstances, I make that be 1, but the numbers are a little big, so I'm going to make that be 2. So I'm going to make the one that's usually half be 1. So 0, -6, 1, -5, 2, -2, right there. Yeah. 3, 3, 4, 10. Okay, so that's the right side. And then the left side is easy to do because, well, the fact that it's a palindrome means that we should just be able to reflect those points over to the other side. So there we plotted 9 points, but if we plotted 9 million points, then this is what we would see take shape. Of course, we've seen this shape enough times that we've given it a name. The name of that shape is a parabola. Okay, good. But now, on the first page of today, we were talking about injective, surjective, and bijective. So the point of today is that here's the first time we've plotted a function. It's not the first time we've plotted anything, but just the first time we've plotted a function. The point of today is to observe, oh, you can plot functions. That's kind of obvious. Then the next thing is that, okay, then what do injective, surjective, and bijective mean if you're looking at a plot? That's the point of today. All right. So I'll ask as a question right here, question 3, for this particular function, what is its domain? All reals, right? Because the domain was not explicitly specified, the domain is the natural domain. So the domain is the reals. And again, this is because the domain was not explicit. The domain is the natural domain of x squared minus 6 which is the reals. Okay. Question 4. what is the range? All reals. Now, why is the range all reals? Right. Because the range is not explicit, there's no calculation necessary, right? For domain, there's calculation necessary. Like you got to figure out some stuff. But not in the case of range. The answer is that if you don't say, everything's in the range. Because the range is not explicit, the range is the reals. So again, to give a vending machine analogy, that would be like if you ordered a vending machine from a company, and the company was owned by a mathematician, and you on your purchase order you didn't say the range, you didn't say the things that are supposed to be in the range, then when you get it back, everything's going to be in there, right? And the mathematician might say something like, well, I have no idea how you're going to feed all those giraffes inside of that vending machine you got there, but I did it. Everything's in there. Okay. Here's a different question. 5. What is the image? Now, this requires a little bit of work. This requires a little bit of work. Okay. Well, let's ask a few feeler questions. So, is in the first place, image, thinking of this as a machine, this is to remind you, this is the set of outputs which can be obtained. Okay.
Can I take a guess?
Okay, what?
That it's y is greater than or equal to 6.
Almost. You made one slight. I don't know if you made a logical error or if you made a speaking error.
Okay.
It's not 6. It's
Oh, 2, 4, 6. I thought that was the lowest.
negative 6.
Negative 6. Yeah.
So,
Thank
okay,
you.
good.
Yeah.
No, that's what I meant. I wasn't sure if you.
Yeah. No.
Okay, good.
Wouldn't.
Okay, so here's a question visually now. Is y equal to 3 in the image? Okay. So now this question can be answered in two ways from what's written on the page. So from the table point of view, the question is is 3 in the f of x row? So is it? It is, right? It's right there. So the answer is yes. From the table point of view. Now suppose that we don't have the table, or we obscure the table, or what have you. From the plot, you could ask the following. Let's draw the line y equal 3. So here's the line y equal 3. And now the question is, does y equal 3 intersect the plot of y equal f of x? So does it? Twice, in fact, right? And how many times does 3 appear in the f of x row in the table? Twice. So the answer to the question, well, the question was, is y equal to 3 in the image? So what's the answer? The answer is yes. For either one of those reasons. How about is y equal to negative 10 in the image? No, it's not. Now, from the table point of view, it's more difficult to tell, because after all, we only listed 9 values. So it's definitely not, negative 10 is definitely not in the table, but there could be other values that we didn't list. However, let's plot y is negative 10. So where is, when you plot y is negative 10, where is it? Very good. And the question is well, does Gesundheit, does y equal negative 10 intersect y equal f of x? So does it? The answer is no. And there's nothing special about negative 10, but well, let's wait a second, just a moment, to make the vending machine analogy. To make the vending machine analogy, what we're saying is that well, because the range was not specified, everything is in the vending machine. It's all in there. Is there a button that you can press? You walk up to it and say, "Oh, I see a delicious 3." Is there a button you can press to get the 3 to come out? Yeah. In fact, you can press that button. That input would provide output 3, and so would this one. Those would give you a 3. Those inputs, those buttons would give you a 3. Whereas, because the range is all reals, negative 10 is in there. Like you can go and look at it and say, oh look, there's a negative 10. But then you try and figure out, is there a button that would give me a negative 10? And the answer is no, there isn't one. Fine. So as a result, we can say that the image is what? So,
Does not include negative 10?
well, I agree, but now I want to know what is the set? What is the set that is the image? That is to say, I want to know the set of all, consider all conceivable horizontal lines, which ones will intersect. So you said it before.
Yeah.
Negative 6 to 10. Sorry, negative 6 to
10, right?
to infinity. Right? So the conceptual device is, well, grab hold of this horizontal line and wiggle it around. You can see that if I stay down here, there's not going to be an intersection down here. But in fact, if I go up to negative 6, I get an intersection. And then no matter how far I move up from then on, there's always an intersection. So this is like a vending machine that has, you know, visible is every real. But in fact, you can only obtain outputs from negative 6 on. It's not possible to get a negative 10. Why would they manufacture it that way? Okay. So continuing this question. Is the function injective? So again, the question is, well, in terms of vending machines, to be injective means that every output that can be obtained can be obtained in exactly one way. So is it the case that every candy bar can be achieved with just one button?
No,
No, right? Why not?
because there are multiple X options. They don't give you the same parabola.
Because it's a parabola, right? Okay, so then, so the answer is no, because, well, you could say inputs, well, I'll say it like this, output 3 is obtainable in two ways. With input -3 or input +3. But to be injective, it needs to be the case that every output that can be achieved in one way. Is F surjective? It is not. Why not?
Saying get -6.1.
Right, okay, good. So the answer is no, because -6.1 is in the range, but no input produces it. Right. But no input produces. Okay, good. So then, is it bijective? No, right? Because to be bijective means it has to be both injective and surjective, and in fact, it's neither one of these. All right, good. So now, I hope that the vending machine analogy is helping, right? We kind of like the vending machines that are not confusing, right? If something's on display, I ought to be able to get it. But if that's not the case, then the thing is not surjective, and that means that the range is not the image. If something is obtainable, then there ought to be just one button that gives it to me, not more than one button. If there's more than one button, that means that the vending machine is not injective. So we like the least confusing vending machine is a bijective one. All right, good. So now, summarizing that example, given a function f, how do I want to say it? You can tell if f is injective from its plot. It is injective when, and so now I'm going to give myself some space to write something, and now I'm going to draw 3 examples. So there's a function. Here's another function. And here's another one. Okay, so as a reminder, with vending machines and generally thinking about functions as machines, the input axis is this one. So inputs are here, and outputs are here. So suppose that you and I walk up to this vending machine here, and we can see, we look at the outputs, and I say, oh look, that's my favorite candy bar right there. That's it. Among the outputs, is there an input? Is there a button that we can press to get it? How can you tell? Right. Draw this. And now the question becomes a visual question. Is there an intersection? There is. So that means that if I press that input, then I'll get my output that I want. But now here's the question: is it the case that every output is obtainable by exactly one input? Not every one. It's true about this one. There's no other button you could press. But if you say, oh well, I see that you like that one, but I don't like peanuts. So here's my favorite one right here. Notice that that output, how many different inputs can you use to obtain it?
3.
3, in fact. So you could press that button to get it, that button to get it, or that button to get it. So is this vending machine injective? It is not. So this is not injective. So the conceptual model is this. You take a horizontal line. To be injective, what must be true about all horizontal lines?
It cannot.
Okay, so you're almost there, but there's a slight mathematician quantification there. When every horizontal line intersects the plot, intersects y is f of x at most once. Okay, so we need to finish this and then we'll be done for today. So how about this one? How many times does that horizontal line cross this one? Once, right? And can you see that if I wiggle it around and I come down here, everywhere that's sort of in here, there's just one. All right? But because the range was not explicitly specified, that means that the range is all reals. So that also means that for example, this item is on display. That one right there, you can't really see it. That one right there is on display. Is there an item is there a button you can press to get it? No, because look, up here. Well, is there an intersection? There isn't one. So that raises the question: is this injective or is it not?
If the range is all reals, then no. It's injective.
It is injective. So yes, it's injective. That means that every item that is on display can be obtained in at most one way. Surjective means every item on display can be obtained in at least one way. So this is injective, but it is not surjective. Finally, just a similar thing here, just to show you that it can be different all over. So for this one, every conceivable horizontal line crosses 0 or 1 times. So is this injective? The answer is yes. Good. So that's all that we have time for today. So I hope you have a wonderful Monday.